In this video, we're going to talk about polynomial and rational inequalities. There are two very popular ways to solve polynomial and rational inequalities. One is to use its graph, and the other is to do it algebraically. And of course, you're welcome to do a combination of the two if you wish. So let's first start off with a polynomial inequality. Now, I know it's a polynomial inequality because it says it in the title, but also I know it's not a rational inequality because there's no fraction here. So the function that we're working with is x plus 3 times x minus 1 squared is greater than 0. So it's in factored form. That's going to tell me that I have a 0 at negative 3 that's going to cross because it has a multiplicity of 1, and a 0 of positive 1, and it's going to bounce because it has a multiplicity of 2. So end behavior is x cubed, which is great. So if I want to know where this function exists greater than 0, that means when y is greater than 0, because it's saying like the function is greater than 0, I just look above the x-axis. So I've highlighted those places, and I have to be careful to not include where the function touches the x-axis because it's greater than 0, not greater than or equal to. So equal to would include what's on the x-axis, but that means I'm not going to include negative 3 and 1 because it's not equal to. So that means that this function is greater than 0 or exists above the x-axis between negative 3 and 1 and from 1 to infinity. So that's an interval and that's in set builder. And that's it, graphically, that is. And now here we have a polynomial inequality that we're going to solve algebraically. So not quite as easy as graphically, but you got to know how to do both. So our inequality is x cubed is greater than x. I know it's polynomial, obviously the title says so, but there's no fractions here. So the first thing I'm going to do is I'm going to get all of my x's to one side and get 0 on the other. So when I move my x to the other side, that's the choice I made, I've got x cubed minus x. Could you move the x cubed over? Of course, but then you're working with a negative x cubed, and that's not my favorite, so. But you can do it. And so what I'm going to do is then set it equal to 0 at this point and factor what I can. So they both have an x in common. Pull it out, I get x squared minus 1. I can factor x squared minus 1 into x plus 1 and x minus 1. So I have 3 x-intercepts here. Now that's going to help me figure out where this thing is either going to exist above or below the x-axis. I like to use a number line to solve these inequalities. So what I do is I take all of my x-intercepts that I've found and I put them on the bottom. Could you put them on the top of your line? Sure. And then what I'm looking for is what output that will give me. So if I plug in negative 1 or 0 or 1 into this function, it's going to give me 0. They're the x-intercepts. We know this. So then what I need to do is test numbers between and on the outside of these numbers. So maybe negative 2, negative 0.5, positive 0.5, and positive 2. So what I'm going to do is throw those into this function, and it's going to tell me whether or not I get a positive result or a negative result. So here's how I do it step by step. Like I said, I'm going to put negative 2 here because it's less than negative 1. You could have put negative 1,000, doesn't matter. But what I'm going to do is plug negative 2 into this function. So negative 2 cubed minus negative 2, that gives me negative 6. So that means the result, or the y value, is negative. So that means that from negative 1 to negative infinity, essentially on the left side of negative 1, that means that my function is going to exist below the x-axis. So not what I'm looking for. So let's figure out the rest and see what we get. So when I plug in negative 1/2, I get a positive result. When I plug in positive 1/2, I get a negative result. And when I plug in 2, I get a positive result. So for our intents and purposes, we don't care what the number actually is. We just need to know, is that result going to be positive or negative or 0, or will it not exist? So what I've determined is that this thing is going to be greater than 0 or above the x-axis, or positive, however you want to think about it, between negative 1 and 0 and between 0 and infinity. So we can write that in interval or set builder notation. And remember, it will not have brackets or less than or equal to or any of those kind of symbols because there's no equal to there. So when you go to graph this, you can graph x cubed minus x, which is the thing that we found when we moved x over. And here's the cubic, right? And it exists above the x-axis between negative 1 and 0, and then from 1 to infinity, which is what we solved for algebraically. As well as, this is what Desmos will give you when you plug in the actual inequality. So parentheses -1, parentheses to 0, parentheses at +1, going on forever. That's how you read that. All right, now let's switch gears to rational inequalities. So I know this is rational, one, because duh, it's in the title, but also we've got a fraction. We've got a variable in the denominator. That's a rational function. So looking at its graph, it looks like we have two vertical asymptotes at 2 and -2, and it looks like our horizontal is at y = 0. We could have analyzed that, but you know, we've got the graph here. So let's figure out where it's greater than or equal to 0. So when I analyze a graph of a rational function, looking for where this thing is greater than or equal to 0, I'm looking for where the function exists, so where these blue curves exist on and above the x-axis. So if I go from left to right, this piece, nah, that's totally under the x-axis. That's not going to count. But starting at -2 and not including -2 because duh, it's a vertical asymptote, it won't include those points. So from -2, not inclusive, we go to 1 inclusive because it's greater than or equal to, so we can include 1. And then this exists below, so we can't really do anything about that. And then we look to the other vertical asymptote, which is at +2. And again, just like -2, not going to include it, but can start at 2, not including, and go on forever because that function is just going to keep on going. So let's write that out. So this thing's going to exist starting at -2, not inclusive, go to 1, inclusive, and then start back up at 2, not inclusive, and go to infinity. So that's interval, and if you want set builder, well, there you go. And for our last example, yes, I did say last example, let's take another rational inequality, but let's solve it algebraically instead of graphically. So I have a rational inequality. I know that because I have a fraction and I have a variable in the denominator. Classic rational function. So we've got x - 1 over x + 2, and that's going to be less than or equal to 0. So there's nothing for me to factor on the top or the bottom, but what I want to do here is find out where my x-intercepts and holes and or vertical asymptotes will exist. So remember, when you set the numerator at the top equal to 0, those are your x-intercepts. So x - 1 is equal to 0. That gives me an x-intercept at 1. And then my vertical asymptotes are the denominator set equal to 0, so that's going to give me x is equal to -2. So going to do the same thing that I did with the polynomial function. Algebraically, is set up a number line. So these two values I have, 1 and -2, go down here in the bottom, but the outputs are different. So if I have an x-intercept, just like with a polynomial, it's going to be 0, because y = 0 when you have an x-intercept. But a vertical asymptote is not going to exist, so I'm going to throw in this symbol here, which means undefined. So now I'm going to choose numbers between and on the outside and see if I get a positive or negative result. So I plug in -3, again, doesn't matter which number as long as it's less than -2, and I get a positive result. I plug in 0, I get a negative result, and I plug in 2 and get a positive result. Also, side note, usually when you have a rational function, and whether you're testing between intercepts or asymptotes or holes, you usually get this kind of cadence of a plus minus plus. Sometimes they're the same, like this could be plus and that could be plus, but usually they alternate. Not always, but it's a nice pattern to look out for. Anywho, we are looking for where the function is less than or equal to 0. So that means we are looking for negative. So I always like to circle my x values at the bottom because it's very easy to trip up and use the numbers you plugged in instead. So that's a tip for you. And I like to highlight where my inequality actually exists as well. Also another tip. So in interval, it's going to start at -2 but not include it because it's a vertical asymptote. It will never include asymptotes or holes. And then it will stop at 1 and it'll include 1 because it's less than or equal to 0. And then in set builder, if you want it. And then looking at the graph of the rational function here, x - 1 over x + 2, we see that the only place that the function exists below the x-axis is starting at 1. And then going down this way. So starting at -2, not inclusive, vertical asymptote, and then going up to 1. Also, if you wanted to graph the inequality on Desmos, it will not include 2, but it will include 1. That's why there's that bold line. One last thing before we sign off, but if you are a summary person with steps, take a screenshot here, print it out, whatever you want to do, it's here for you. All right, that's going to do it for this video. Thank you so much for watching.